Alright, we're throwing ourselves right back into part 2 of this video. You can tell it's part 2 now. So, graphing polynomials part 2. This is the part where we actually graph them. This is the same polynomial we worked with in part 1. If we're going to graph the polynomial, we need to think about two broad categories of thing. The two things we need to think about are local behavior. Local behavior basically means when x is small. And we need to think about end behavior, which basically means x is large. I'm going to start with local behavior because that's the more easily accessible of these two things. Local behavior consists of two basic pieces. Local behavior is going to be x-intercepts. Let me put end behavior a little further down. Give myself more room here. Okay, local behavior has two pieces. X-intercepts. X-intercepts mean places where the function is going to cross the x-axis. If your function is crossing the x-axis here, that means y equals 0. That's what it means to cross the x-axis. So that's what x-intercepts mean. Y equals 0. You can probably guess what the other piece of local behavior is. It's y-intercepts. Y-intercepts mean you're crossing the y-axis, and then you have x equals 0. That's what it means to cross this axis. Your x value is 0 on that axis. And then end behavior is what happens when x is very large. I will get to that in a little bit. First, I want to talk about x-intercepts and y-intercepts. I think I'm going to have to erase this for room. Good thing this is recorded, and if you needed to look at it longer, you can just rewind the video. Okay. Let's talk about x-intercepts first. X-intercepts mean you set y equal to 0. So to start this off, it's actually very simple. You set y equal to 0. If this is y, and I make y equals 0, this is the equation I get. Astute observers will note that this is a quadratic equation. And if my goal is to solve the quadratic equation, you have to set one side of the equation equal to 0 and factor. That's how we solve quadratic equations. This should be review from algebra. Once you set y equal to 0, you no longer have two variables here. You only have one variable left. It's just x, which is good because we want to know where x equals 0. So that's the goal of this, is to solve this thing for x, to discover where x equals 0. That'll give us our intercepts. And again, quadratic equation, it's already equals 0. All you have to do is factor it, solve for x. This guy factors into 0 equals x minus 4 and x plus 2. Negative 4 and positive 2 will multiply to give us the negative 8, and they will add to give us the negative 2. So these are my factors, which means that the x values I get when I set these equal to 0 should be positive 4 and negative 2. So I have two x-intercepts. Here's the very important thing to keep in mind about x-intercepts. X-intercepts are points. That is the kind of mathematical object that an x-intercept is. An x-intercept shouldn't just be a number. It's not like a quantity of something. An x-intercept should be a position on a graph. That means it's a point. So, ideally, I don't want to express my answer as a list of numbers. I want to express my x-intercepts as a list of points. 4, 0 is a point. Remember, this all happens because I set y equal to 0. And 4 is the x value that gets me there. And negative 2 is the other x value that gets me there. These are my x-intercepts. I'll call them x-ints. So that's all there is to that. Finding your x-intercepts, honestly, is going to be the hardest part of graphing polynomial functions. X-intercepts are always going to involve a process of setting your polynomial equal to 0 and factoring. There's going to be a lot of factoring in your future. We're going to factor polynomials for days, and then when you're sick of polynomials and you hate them and you don't want to do them anymore, we will move on to rational functions. And in rational functions, you'll have to do twice as much factoring because you'll have to factor the top and the bottom. It's going to be great. It'll be an exciting time. I'm looking forward to it. But for now, we're just going to do polynomials, and graphing polynomials means finding the x-intercepts by setting it equal to 0 and factoring. To get y-intercepts, my markers aren't, all my markers are on the verge of death. I have to rotate often to keep them legible. Y-intercepts. Y-intercept means x equals 0. Setting x equal to 0 is, typically speaking, much easier than setting y equal to 0. You just take your y and you plug in zeros for x's. So 0 squared minus 2 times 0 minus 8. Y is negative 8. That's it. Once again, ideally, this should not be a number. This should be a point. An x-intercept is a position on the coordinate grid, so we should express that as a point. Our y-intercept is 0, negative 8. Started with us setting x equal to 0, negative 8 is the output. This is my y-int. Good. So that's my x-intercepts and my y-intercepts. The next thing we need, I'm going to have to erase all of this. Let me write down these points real quick. 4, 0, negative 2, 0, 0, negative 8. This is my local behavior. These 3 points. And there's other points you could get. Like you could make a table of values if you wanted to. I am not interested in making a table of values. I want very carefully chosen points that are the most meaningful, the most important, and those are the intercepts. I kind of don't care what this function is doing when x is like 2 or 1. Those aren't intercepts, so I'm not interested. So this is my local behavior. Next up, I need end behavior. And end behavior means what does y look like when x is big? And we have to pause for a moment here so I can qualify what I mean by big. I don't mean like a couple hundred. A couple hundred is not big in the grand scheme of things. When I say x is big, I mean billions, trillions, quadrillions at a minimum. That's what I'm talking about when I say x is big. So when x is big, let's start on the smaller end of big. Let's say if I want x to be big, let's examine what happens when x is 1,000,000. If x is 1,000,000, then I should plug that in here. 1,000,000 squared is 1,000,000,000,000. So this term by itself will be 1,000,000,000,000. This term will be minus 2,000,000, which we could do that in our heads. 1,000,000,000,000 minus 2,000,000 is, that's 1,000,000,000,000 actually. Rounding to the nearest number that matters, it's still 1,000,000,000,000, right? Like, here's 1,000,000,000,000. That's 12 zeros. If you subtract 2,000,000 from that, that doesn't matter. Like, the size of this number has not changed in any meaningful way when you subtract 2,000,000 from it. Like, you could write it, I guess. It'd be a bunch of 9s here. 9999980000000. Like, this number is effectively still 1,000,000,000,000. It's 0.0002% away from being 1,000,000,000,000. So at this point, you can effectively just round it and say that this is about 1,000,000,000,000. So when you plug in 1,000,000, this term is 1,000,000,000,000. This term is irrelevant. It honestly does not affect the size of this number at all in any meaningful way. This number is laughably small. Like, you want to take this number and subtract 8 from it, no one cares. You still have 1,000,000,000,000. If you think about this in terms of dollars, if you have $1,000,000,000,000 and someone asks you for 2,000,000, like, that does not change your net worth in any way. So the moral of this story is, and what I'm getting at with all this is, when x is big, your polynomial always looks like just the first term. This 2x and this -8, they don't matter. On the scale that we're talking about, they are rounding error. They are chump change. They are completely irrelevant. The only thing that actually matters in terms of what this function looks like is what's called the leading term. So when x is big, y looks like x squared. X squared should be familiar to everyone. It looks like this. It's a parabola. You all know x squared. It's very straightforward. The thing about this graph looking like this is, it only looks like this when x is big, which means all this stuff in the middle here, I don't care about. All I'm interested in is the ends. This is the x is big region of the graph. The far right and the far left, that's x being big. This middle stuff, that's local behavior. I did different math to figure out what that stuff is. This end behavior, all I care about is the two ends. And in this case, the two ends are going up to the right, up to the left. I think I got those directions right. I'm facing backwards from you into camera. Yeah, this is your right, and this is your left. Yes, anyway, it's going up in both directions. This is a kind of end behavior that I call the field goal. It looks like this. My dad referees a lot of high school football, so this is the field goal gesture. End behavior is a field goal. That's x squared. So with this information, I can put it all together with this end behavior and this local behavior to draw myself a graph. End behavior is the field goal. which is up to the left, up to the right. Okay, time for a graph. That's not visible at all. Let's see how well green shows up. Oh, that's nice. I think that's nice. Yeah, that's coming in the camera. Good. Okay, so here's what I know about this function, for sure. I know it crosses the y-axis at -8. I know it crosses the x-axis at -2 and at 4. And I know that the end behavior is up to the left and up to the right. So now I'm just going to connect the dots with these arrows. Oh, I missed. That's fine. There you go. This is my polynomial. -2, 0, 4, 0, 0, -8. Up in both directions. That's the whole thing. More coming soon.